problem 1.2, I'm going to put it up here on the screen so you guys can see it. This time I really will put it. Last time I didn't, but I got a new setup. And tell me if y'all like it. So problem 1.2d says determine the energy spectral density of a square pulse x of t equals rect of t divided by cap t, where rect of t of cap t equals 1 for t in between minus t over 2 and positive t over 2 and equals 0 else. So we calculate the normalized energy E of x in the pulse. So what we have is a function. It's called x of t, and it's rect. So rect stands for rectangle, and it's 0 for t greater than or equal to 2, and 0 for less than t minus t over 2, and then it's 1 in between these bounds. So the total distance is cap t, and so then this equals rect time divided by the distance of this rectangle. And they want us to find the energy, and they want us to find energy spectral density and the normalized energy, I believe. Yes, the normalized energy in the pulse. Alright, no problem. So let's find the normalized energy. So the normalized energy is going to be E of x is equal to the limit from minus infinity to infinity of x squared of t d of t, right? So x squared of t in this case is rect t, cap t dt from minus infinity to infinity. Well, we know this is 0 from minus t over 2 to infinity, and is 0 for t over 2 to infinity, so we can change these bounds. This goes from now minus t over 2 to positive cap t over 2. And then in between these bounds is 1. So it's 1 here, because the height of this width is 1, so it'll just be 1. It's a constant 1 in between these two, these range here. And then what we do is we take the antiderivative of 1, which is t, and we put the bounds. Once we calculate this, it becomes t minus negative t over 2. So 2t over 2, which turns into t, right? That's simple. Alright, let me just make sure the video's looking good. Okay, just want to make sure everything's looking good over here. Alright, perfect. So that's the solution here for this problem, for the energy. So this is going to be the normalized. Now they want us to calculate with energy spectral density. So every energy signal has energy spectral density. Every power signal has power spectral density. So this is an energy signal. And a computer energy spectral density, what you need to do is first take the Fourier transform. So an energy signal, I'm going to just denote as Ex of t. The Fourier transform of rect is sync, and we can prove that using a table, or you can derive it by hand. I'm gonna put a table somewhere over here, and you guys can reference. So this is sync. This is gonna be sync f of t, cap t. All right, not we're in the Fourier domain. There's no lowercase. There's only f. And then now what we need to do is take the absolute value and square. Let's take the absolute value of sync and square, which results in a t squared, sync squared f of t. Alright, so we just found this. This is the energy spectral density, and the representation, that function is represented with a psi. It's a Greek symbol. Don't hurt me, I forgot the Greek symbol wrong. That was never my strong area. So that's the answer for problem 1.2. So now we're going to move on to problem 1.3. And what I wanted to do for problem 1.3 is I kind of wanted to skip it because there's a really good proof I found online. So problem 1.3 is a proof about proving the average normalized power in terms of its periodic average normalized power in terms of its complex Fourier series coefficients. And there's a very good proof by a gentleman online. Oh, whoops, I don't know why I did that. My marker actually has a eraser on the back of it. On a website online called Tutorial Point that I really like to use. And I was thinking just having that link to that tutorial, because it was really, really, really informative, really, really good. So I think that would be beneficial to put the link on there for his little explanation of how you would go about proving that. And the proof is not that in depth. You have to use Parseval's theorem and some other things, so it's not too in depth. But I'm going to leave that one. I'm going to link that 1.3 in the comment section. I'm going to move on to the next problem. So the next problem says, using time averaging, find the average normalized power in the waveform x of t is equal to 10 cosine 10 of t plus 20 cosine 20 of t. So they want us to find the average power. So we know it's a power signal. And the function is x of t is equal to 20 or cosine 20t plus 10 cosine 10 of t. And they made note here, I believe, that T naught is equal to 1 over F naught. And F naught is equal to this divided, whatever this is in here, divided by 2 pi. So that's going to be 10 over pi for this one. And so this is F naught for that. And then for this one, this guy is going to be 10 over 2 pi, so you get 5 over pi. So that's both of their periods, and this is going to be important here in a little bit. So we know that the power, the average normalized power of a power signal is the 1 over t, so 1 over the period, times the integral over 1 period, so minus t over 2 to cap t over 2, of the signal, so x of t squared dt. So now we're going to have to square this function and compute its power. And it looks a little difficult, but there are some tricks here. So first, we got 1 over cap t, then we got the integral. Okay, so now I'm going to do this in my head, but you follow with me. So we're going to multiply this part here by multiply by a version of itself. So this is going to be 20 cosine 20 of t times 20 cosine 20 of t. So that's going to be 400 cosine squared 20t plus, you're going to get 2 cross terms, so it's going to give you 200 plus another 200, that's going to be 400. It's going to be cosine 20t cosine 10t, because we're multiplying these two together and then the amplitudes multiply, but we can't multiply these together inside because their frequencies are different. And then we have the last term, which is 10 cosine multiplied by itself. And so this is going to be 100 cosine squared 10t dt. And you're probably looking at this like, this looks difficult, but it's not too bad. So first, before we move on, we're going to use a couple of properties I'm going to write over here. The first property is when you take the integral of a cosine squared over its period times 1 over its period with the appropriate frequency that correlates to its period on the inside. So this would be like a 2 pi f of t. You end up getting 1/2, and there's an amplitude out front, and you get a over 1/2. Another property we're going to use is cosine of x times cosine of y is equal to, this is trig now. Now we're getting trig. I don't know if you guys like trig or not, but so this is a trig property. Cosine x is equal to cosine of x minus y plus cosine of x plus y, all that divided by 2. So we're going to use these two properties to solve. We're going to break it up. So we're going to break it up over here. I'm just going to start putting cap t, but you guys know cap t means minus t over 2 t over 2. It's going to be 400 cosine squared 20t dt plus the integral 1 over t cap t of 400 cosine 20t cosine 10t plus 1 over t, the integral cap t of 100 cosine squared 10t dt. Alright, so let's deal with all these individually. So what I'm going to do is I'm going to erase the board, and I'm going to solve these going this way. Going this way. This problem's not that bad. It's just more about the calculus. It's not really like a deeply intuitive question or where it requires quite a bit of forethought or anything. It's just more about can you do calculus well. So this part is going to evaluate this cosine square. It's going to use this property here. This is going to be 400 divided by 2, so that's going to be 200. Over here, we're going to get cosine squared. Down here, we're going to get 100 divided by 2. That's going to be 50. So we're going to add those together. Over here, what we're going to get is a cosine of. So let's just put this one over here. We're going to get cosine of minus 10t plus a cosine of 30t, right? So we're adding 10t, 20t plus 10t, 30t. It's like 3x plus 2x, 5x, and yeah. And then so we get this. Now we're going to use another property. Which I'm going to put it here in the corner, put in a little box. So when you have 1 over t of the integral over the period of a cosine of 2 pi f of t, you actually end up with 0 because you're integrating over the period of cosine, one period of cosine with the negative and the positives, and so they're going to cancel out, so you end up with 0. So these two integrals are going to end up being 0. So 0 here. And then we're going to add these together up here, and we get 250. So the average normalized power, or the average normalized power for this function is 250. And specifically, we want to be specific about the units. Usually it's watts, but that's not really a necessity. So that's the answer. That's how you do that one. You can go through the math, or there's just some tricks that help you solve it, but you always remember that these two integrals compute to this thing, then it becomes easy. All right, 1/2, and then you have an amplitude. Here we have an amplitude, so it's 400 times 1/2. So you can factor out this 400, and then here you factor out 100, and this whole thing would be 1/2 and multiply by 100. So you end up with 250. So that problem's not too bad. So let's move on from there.